There are three outcomes when we combine chemicals. The first one, the most fun one, right, is a chemical reaction. Like if we take methane, CH4, and oxygen and put them into a combustion reaction with each other, they will rearrange and form CO2 and H2O. We can see here that the atoms and the molecules rearranged. We got completely different substances, CO2 and H2O, than we started with, CH4 and O2. And we get these G-trap signs of chemical change, gas, color, heat, odor, precipitate, that tells us that a change had happened with those molecules. So if I take this vinegar and baking soda and combine them, we can see they start to fizz and bubble. This is a reaction, a chemical reaction occurring, where the atoms are rearranging, and the gas produced is evidence of that. The second thing that can happen when we mix chemicals together is that we would say they don't mix. Scientists would say that's an insoluble mixture. Like when we take water and sulfur and we put them into a container, you would just wind up with water and sulfur. The same substances are present as they were before you put them together. The molecules are not rearranging, and the substances will often layer out based on their density because they did not react with each other, and they have those different densities. So we can see here water 1.0 and sulfur 1.96. If we were to put sulfur in water, the sulfur would sink to the bottom of the water and just hang out on the bottom there. No dissolving. You can see here with this fancy homemade lava lamp that when you have oil and water mixed together, that you can shake them up and they won't mix either. We call this type of insoluble mixture a heterogeneous mixture. Hetero means different, so what this means is that we can easily see the different parts of the mixture because they're not evenly mixed. All the particles are not very well mixed together, like water and sulfur or oil and water. The third type of outcome that we can have is a solution. Like if we take water and salt and mix them together, we get, guess what? Salt water. In this solution, the molecules have not rearranged. Nothing broke apart and then reattached into new forms. The original substances are still there, but the key is that they are not easily distinguishable from each other. When you look at salt water, it's not really clear that there isn't salt in the water. You can't see it separately. Like when we take the salt here and shake it around, it's as if the salt has disappeared, but it's still there. It's just hiding and evenly mixed, and we call this a homogeneous mixture because everything looks the same. And so I like to think of solubility as dissolvability because that's what it is. And it's sort of like particle hide and go seek. The key is that there's only so many hiding places. So eventually you're going to get to a point where all of the hiding places among the water molecules have run out. And this is when you reach a thing called saturation. And when the substance runs out of a place to hide, then all of that solute will just fall to the bottom of the mixture. And typically that's what we'll see. Our undissolved salt particles, in this case, will fall to the bottom, and the rest of the salt has taken all of the hiding spaces up above. When a solution is saturated, like this saltwater solution, we can see that the undissolved particles are at the bottom of the container, undissolved. Basically, solubility equals dissolvability, and it varies by substance. Like we've seen, salt will dissolve in water, but it won't dissolve in oil. So, if we put a bunch of salt into a container of oil, it does not matter how much we stir it, how much we shake it, how much we heat it up, that salt will not dissolve in the oil. So salt is water soluble, but it is oil insoluble. One of the uses of acrylic is for fake fingernails. And so it needs to be water insoluble so they don't dissolve when you wash your hands, but if you need to take them off, you can use acetone. Got an oily mess to clean up? You better use an oil-based cleaner, because water-based cleaners are not going to clean up an oily mess, they're just going to slosh it all around. If you have a water-soluble mess, like sticky messes, then you could definitely use a water-based cleaner, like ammonia, where the ammonia is dissolved in the water. And so a lot of cleaning products are made based on the types of messes that they're made to dissolve. Vitamins have different solubilities as well. Vitamin C, we can see, will drop in that water, and vitamin D is this really like oily substance that comes in a capsule. So I can take this vitamin C and stir it up and dissolve it in the water because it's a water-soluble vitamin, but vitamin D is not a water-soluble vitamin. It is an oil or fat-soluble vitamin. And so the key is that this type of vitamin will build up in people's tissues. So people have to be very careful with the amount of vitamin D that they take, because you realistically can overdose on vitamin D because it does not dissolve in the blood, so the body can't really clean it out very effectively. Whereas vitamin C does dissolve in the blood, which is water-based, so if you take too much vitamin C, you just urinate the rest of it out. Let's see if we can identify things as soluble, insoluble, or chemical reactions. Here I have some glitter and water. What do you think? Now I have some furniture stain in water and the furniture stain in some mineral spirits. Here is oil and water and vinegar with some phenol red. It's normally red, but look, it turned yellow. What's going on there? Here we have oil and salt. We talked about that one. And some food coloring, green food coloring, turned the water green. Salt and water, we've talked about as well. What kind of combination is that? And then usually iodine is kind of yellowy, but when we put it in starch, oh my, it's purple. So now you should be able to identify which of the three things are happening when we combine chemicals.